including next token prediction and full sequence generation is paramount. Implementation of positional encoding to incorporate sequence order and transformer models. Um, Develop and apply. Okay. Is it good now? I mean, you want to hear. Okay. Okay. So again, going over all this stuff again, you got to implement self-attention and scale dot product attention MHA from scratch. You got to understand some fundamentals in language modeling, including next token prediction, full sequence generation. You have to implement positional encoding, which I believe we have also seen in some of the previous homeworks. Hopefully, it should be easy. Develop and apply causal and padding masks, which also we have seen in previous homeworks to enforce autoregressive behavior, and obviously handle variable length inputs and use a fixed length, rather converting it to a fixed length. Explore multi-head attention and its ability to capture multiple dependencies in the input sequence. Implement key transformer components such as self-attention layers, feed-forward layers, and full decoder layers. At the end, you'd be training a causal transformer decoder model for autoregressive text generation, basically. And you'd be generating text samples using the trained language model to basically evaluate its qualitative performance. And that's how we're going to calculate the scores for you guys too. The setup and workflow is as follows. There's a test suite integration. The code is going to be tested in a manner which is very similar to the other homework part ones. You can basically run this locally, so you should be able to perform most of your initial development locally without having the need of any external compute resources. But from my experience with this homework and also this is kind of a shared experience with people. Some people actually found the CPU not good enough for this, so they actually ended up training homework part one, or homework for part one even on Kaggle. So just be aware of that. There's some hands-on experience which is presumed. This assignment provides an opportunity to build an end-to-end deep learning pipeline. So we'll be substantially reducing the number of abstractions, basically, hence compared to previous assignments. The handout structure for the zip file is as follows. Um, so the top level directory is what is provided to you as handout directory. Within it sits the data subset and homework for lib, my touch. The tests are for us. The README and requirements.txt is obviously for you. For our provided notebooks to work, your notebook's current working directory must be the same as the handout directory, obviously. So you'll be able to test your code locally using the subdirectory in the handout. As you can also see the structure format on the right hand side of your screen. The main library, which is homework for lib, you will incrementally implement components of this library to build and train basically two models on a high level. So this would be used for part one as well as part two. Part one would ask you to train a decoder-only transformer for causal language modeling, much like GPT. And homework for part two is something when you'd be required to train an encoder decoder transformer altogether, like a complete transformer with encoder as well as decoder. This is for end-to-end speech recognition. That's where the need for the encoder comes in. The handout also includes MyTorch, like we saw earlier. In MyTorch, you'll be basically implementing multi-head attention and scale dot product attention. So this is just for homework for part one here. And you'll be required to add it to your MyTorch collection as we've been adding perennially since the start of homework two. The handout, there are some tests. You'll be provided with a test suite to verify your implementation, which is quite usual for homeworks. One, you do not need to change anything inside the test at all. So please read the write-up, especially page 7. The instructions are pretty clear for different ways of maintaining your handout, so it remains consistent for both parts of the homework, so that you don't face any problems later for part 2. Um, yeah, I think yeah. Who's taking slide 2? Okay, there we go.
Yeah, so I'll take over to the other part, and we're first going to talk about language modeling. So in this homework, we are going to implement transformers, and it's just like we want to predict the distribution among the tokens. So first, we have to figure out what is a token and how do we define language. Um, so in my point of view, the token is just the efficient way to represent words in our computer languages. So some may wonder why don't we just use UTF-8 or characters to represent them? I think it is most because they're too long and there are no semantic ways to do that. So how do we make tokens? We usually just use BPE to divide the tokens into parts and make them into language space, also multilingual ones. So the language model is used to predict the next token. It is mostly about given the previous all tokens, we are going to predict the distribution of the next token, which is a distribution among the logits. And there are mainly two ways of language modeling. First way is decoder only one, and the second way is encoder only one. Encoder and decoder one. I think today mostly we only use decoder only models because they're easy to scale up and train. And the decoder only transformer is used in most modern architectures. I think expect for like Google TIFF, I don't remember what the model is. We all use like decoder only models like GPT or Llama or Gemini or other stuff. And when we train the decoder only model, we only have to train on the next token prediction pattern. So we only have to predict the one distribution given all the passes before. And on the right, it is a really simple um, transformer structure. We can have many improvements here, but not going to include that here. Here is a training example. So we're only going to predict the next token. So the training, we don't have to label them. We only have to like scratch all the data from the web or from the book and just then to learn. So for example, um, actually in the pre-training form, we don't have inputs or targets. Oh, we only have to like input a start of token and I swam across the river, and we just give them all the things before the river and let it to predict the river token. And we also have some special labels like start of token, end of token, just to make the generation do not iterate forever. Whenever it meets the end of token, it will just stop. And the token embedding is like d-dimensional embedding, which is quite similar before. I think in current embedding size, it is mostly about 4096 in modern LLMs. And you can use different embeddings, which map tokenizers into the embedding, which is dense vectors for us to input into the transformers. And the output, as we talked in the start, is just the distribution among the logits. The logit size is the language size, which is the vocabulary size. And here is just a very simple expression of how it works. And lastly, we're going to talk about softmax and cross entropy loss. So we also have to like have the laws to train the transformers. So um, in your code, you only have to use cross entropy loss in the PyTorch. It combines the softmax with the cross entropy loss. The way why they do this is mostly because when you combine them together and when you do your backward pass, it will generate a very nice mass formulation instead of doing like exponential computations. It's just a linear one. And also you can do some kernel fusion with softmax and CE to make it computing faster. So It is a very elegant way to do that, but your mind, you only have to remember that the softmax and cross entropy loss is combined in the cross entropy loss function. Yeah, and before these are all like um, inside the transformers. So when you go outside the transformers, you are going to have the iterative or recursive generation. And you also have, so you get your logits, you get your distribution, you have to sample from them. The simplest way is just greedy decoding. Is you choose the largest logits to decode from them, but you have many other ways to do this. Like beam search, you can search among like the uh, best three or best five space. We can have top K sampling, nucleus sampling, temperature sampling, and other advanced decoding strategies. Just to mention that this is not trained in your code, it's just in the inference time. Yeah, yeah, that's yeah, yeah.
Hi, this is Mani, and I'll be taking over the presentation. So, continuing from where Ixiong left, we'll first talk about attention evolution. So, we all know that the transformer started booming from 2017 because of the paper. Attention is all you need, but that's not the starting point. Like 3 years back, uh, there was like Haranu proposed an attention mechanism which was built on top of that, and we then transferred to self-attention, then multi-attention, and then to cross-attention in case of encoder and decoder. So in homework for part one, we mainly have two tasks. In task one, you will be incrementally building self-attention and multi-rate attention from scratch, and you will be adding them to the MyTask library that you have been developing from like homework one, and that's worth 30 points. And in task two, you will be working with homework for lib package where you will be training a decoder-only transformer model, and that's worth 70 points. So in task one, our goal is to, as I mentioned, that our goal is to build scale dot product attention and multi-headed attention from scratch. And this is a visualization of self-attention. Here we can see query key and values. And like for example, if you are calculating the attention scores for the second input, which is x2 here, we'll multiply query with key, which will give us the attention score. And we'll normalize it using softmax, and then we'll multiply the attention scores, the normalized attention scores with the values, and then we'll get a context vector. And the in previous slide, we saw it for one input token, but we all know that if we are doing one input token at a time, it's really inefficient. So this is the visualization when it's vectorized. Here we can see the query matrix and the key matrix multiplied to give us the similarity score. And the main thing here is the dimensions. Across all the parts in homework 4 P1, you need to pay attention to dimensions. And if something is going wrong, the first thing that you need to look is if there is something wrong with the dimensions. So till now, we took it granted that we have query key values, and then we multiply those and we get attention scores and then context vector. But how do we get query key values from a token? So to get those, we first get an embedding vector from the token, and then we transform the embedding vector, which will give us query key and values. And since it's a linear transformation, we naturally use linear layer to do that, and this naturally leads us to the implementation of linear layer. So you might have implemented this in homework one, part one, but the only drawback of that implementation is we just considered two-dimensional input in homework one, part one. But usually in transformers, we have inputs more than 2 dimensions, which will be of shape, batch, sequence length, and embedding dimension. So it's more than two. So we need to extend the linear layer to make it generic so that we'll be able to handle arbitrary dimensions. Here, the asterisks represent arbitrary dimensions, and in feature is the number of input features. So when it comes to handling arbitrary dimensions, what we do is we just flatten all the dimensions except the in feature dimension. So we flatten everything, and then here we consider it as batch size, which will eventually become 2-dimensional input. And then, as usual, we perform a affine transformation where we multiply with weight matrix and then add the bias to it. And since the input is of arbitrary dimensions, we need to unflatten that back. So we'll unflatten that back by based on the input dimensions, and then we'll give that as output. For this, you can use homework one code as reference, and you can build on top of that. And I would suggest building incrementally because there might be a lot of dimensional errors in this. So try building something. For example, first you can try building forward function of the linear layer and then try testing it. If it's not working, first debug that forward function and then go to the backward function. Don't try to complete everything and test it. And coming to the backward pass, this is same as the homework one, P1, but again, the drawback is we need to handle arbitrary dimensions. So initially, we'll be given the loss with respect to the output of linear layer, and our goal is to calculate the loss with respect to the inputs of the linear layer, weights, and the bias. So similar to what we did in forward pass, we'll just reshape the gradient of loss with respect to the output of linear layer to two-dimensional gradient, which will be of shape, batch size, and output features. And then we'll calculate the gradients as mentioned in the equations. For example, if you want to calculate the gradients of loss with respect to inputs, we just need to multiply the gradients of loss with respect to output with weights. And this will be same for the weights and bias. And once we do that, since the input is of arbitrary dimension, we also need to reshape the gradients to also the same dimensions. So we need to reshape back to the original input size. And the next thing that we will be implementing is a softmax operation. And we have to implement this because this is part of the scale dot product attention process. And again, you might have implemented this in homework one part one. And only extension that you have to do is you have to handle arbitrary dimensions. So here you can see the softmax equations. You just need to exponentiate it, and you need to divide by the sum of the exponentiation. Here, actually, the forward pass is easy because you can choose which dimension to exponentiate on and which dimension to sum on. But the main problem comes with backward. So in backward, we'll be first calculating the Jacobian matrix, and we need Jacobian matrix because softmax is a vector valued activation function where each input will affect the output. So we need derivative of how every input affects the output, and Jacobian matrix exactly captures that. So first we need to calculate the Jacobian matrix, and we can calculate the derivative of loss with respect to the pre-activation inputs by right multiplying Jacobian with the derivative of loss with respect to post-activation output. And if the dimension is more than 2, what you have to do is you have to move the dimension for which you are calculating the softmax to the last dimension, and then you need to flatten every other dimension. And by this way, it will become a two-dimensional input, and using that, you can calculate Jacobian matrix. And please keep this in mind, and this will be the most important thing that you have to pay attention when you're implementing the softmax operation backward function. And once that's implemented, you can go ahead and implement scale dot product attention. And at its core, it's just the implementation of this equation, which you can see on the slide, which is the query matrix multiplied by key matrix, and it's scaled by root decay. And then we'll normalize using softmax, and which is then multiplied with value matrix. And you can also see the shapes of Q, K, and V matrix given below. Here, N is the batch size, H is the head number of heads, L is the length of target sequence, and E is the embedding dimensions. And this might differ depending on what you are implementing. For example, in self-attention, the L and S might be same, but in cross attention, this will be different because encoder and decoder comes into picture. And you might also think that why H is here in scale dot product attention. We have included H because this will be the scale dot product attention will be reused in multi-headed attention. So in order to make the code extensible and reusable, we have included H here. And for now, take my word for it. When I'm explaining multi-headed attention, I'll come back to this and explain why we are including H here. But uh, you can just follow the equation mentioned here and you can get the results. And when you are transposing the key matrix, just pay attention to which dimensions you are transposing because of the H dimension which is present here. And the backward function is also very simple if you understand how scale dot product attention works. In case if you don't understand how it works, I would recommend you watching the attention lectures and coming back to this before implementing this, because understanding it would make the implementation and debugging very easy. For backward, first you need to calculate the gradient with respect to weights, with respect to value matrix. Uh, and similarly, then you have to calculate with respect to attention scores. And attention score is just a uh, it's just a normalized multiplication of query and key. So you just and then you need to calculate the gradients with respect to query and key. And you need to and the return value of this backward function will be gradients with respect to value, query, and key. So once you implemented scale dot product attention, you will be implementing multi-headed attention. So in multi-headed attention, we just split the attention head into multiple independent attention heads, like which is denoted by H. So we do that because we want the model to focus on different aspects of the input, and that's what multi-headed attention helps to do. And how we do it by just splitting first and then doing the scale dot product attention independently on each head, and at the end we concatenate all the outputs of scale dot product attention, and then we pass through final linear layer, and we at the end we pass through another linear layer mainly to mix the information that we obtain through multi-headed attention, and that's why we have a linear layer at the end. So this is a visualization here of multi-headed attention. As you can see, we have multiple attention heads, and each attention head will give us uh, different hidden states, and we'll concatenate it. We'll pass them through linear layer, and then we get the final context vector. So in scale dot product attention, I said that we have to consider the head dimension as well. So let's see why we need to consider it. So for example, if you don't consider head dimension when implementing scale dot product attention, sure we'll be implementing multi-headed attention by looping through each attention head. And looping just causes the program to slow down a lot. So we don't want that. We need to vectorize everything so that we utilize the GPU to the fullest extent. So that's why we take care of attention head dimension and scale dot product attention so that it can be reused in multi-headed attention. So, uh, so this is how we implement multi-headed attention. First, we just use one linear layer. We just use three linear layers to project query key and value matrix. And since we have multiple heads, we need to split the heads, and we just split the output of linear layers based on the number of heads we want. And one thing to keep in mind is that we can't choose arbitrary number of heads. So the model dimension and the head dimension should be divisible so that the output dimension of each head is an integer. Else it would be some floating point number which we won't be able, which is not good. And once we split the head, we also need to take care of masks. So there are two kinds of masks which we'll look into detail in few minutes. But for now, those two masks are padding mask and attention mask. Uh, the attention mask is mainly causal mask, which is to prevent model from cheating, and padding mask is to prevent the model to attend to padding tokens. So we need to merge both the masks, and you will be merging the mask in the merge mask function. And the masks are usually two-dimensional. They have two-dimensional shape, but as you can see, attentions have 4 dimensions. So when you're implementing merge masks, you need to add few dimensions and then you need to broadcast them to the batch dimensions. Just make sure you keep this in mind when you're implementing merge masks. And once you merge the masks, you can reuse the scale dot product attention to compute the attention scores for each head. And once you compute that, uh, you will have output for each head. So, and as we discussed earlier, we need to concatenate the output. So you need to implement the concat heads to concatenate all the outputs, and you need to do a affine transformation using a linear layer. And the backward is also similar to this. I'll explain the backward using this picture. So we'll be given the gradient of loss with respect to the final output. So first you need to backpropagate through the linear layer. You can just call the backward function on the linear layer. And since since we have multiple attention heads which are concatenated, in order for the gradients to float through multiple attention heads, you need to split the gradients so that the concatenated gradients flow through each attention heads. So you need to split it using the split heads function, and you need to calculate the gradients for each scale dot product attention, and you can reuse the backward function from that class. And again, since we are splitting the attention heads from the attention heads initially, we need to concatenate them so that we are able to calculate the gradients of loss with respect to inputs. And this is done using concatenate set. If you notice carefully, the the order in which we split and concatenate will be reverse with respect to the backward function. So this might be a suggestion that might be useful to implement in multi-headed attention backward function. So this is all about task one, and it adds up to 30 points, and majority chunk of the points is in task two, where you will be training a decoder only transformer. So the development phase of this is different from other homeworks, because usually when you're training something, we have given you a Jupyter notebook and all of the development takes place in the Jupyter cells, which makes life easier. But in this homework, we just give you a package and which has multiple submodules with a lot of scripts, and you have to implement certain parts of scripts of each file, which will look. And but the main problem is, since you are used to Jupyter environment, there might be a transition when you are coming to this implementation. But one easy way is to find the entry point of the code and then backtrack it so that the implementation is easier. So let's get into what you have to actually implement. So first, as usual, you need to implement a few things related to data. So first, we'll do some data pre-processing. So first, you have to load the input data into memory, and then you need to split the strings into tokens. And you need a vocabulary, because models won't understand text. You need to convert them to numbers, and then you need to give them as input. So you need to build a vocabulary which converts the text to some index, and in further down in line, you will use that index, which you will pass through an embedding layer to get a embedding of that particular token. But as of now, in data pre-processing stages, you just need to get the index, and that is what is mentioned in point 4. So we mentioned that we need to tokenize in last slide, but we have we have given the tokenization implementation for you so that you don't need to implement. We have given 4 tokenization strategies, and the first one is character level tokenization, and the other 3 falls under subword tokenization, which is done through byte pair encoding. So we can, like, there are 2 tokenization which people usually start with. One is character level tokenization and one is just word level tokenization. The problem with word level tokenization is there might be too many number of words and we can't cover everything in our vocabulary. So usually you end up with a problem called out of vocabulary problem, where you might have not learned a token for that particular word. And the problem with character level tokenization is, since you are dividing the input at character level, where you consider each character as a separate token, it's really inefficient because even in output generation and even in input handling, it's really inefficient because, for example, in output generation, you'll be outputting each character at a time, which is inefficient and it will take a lot of time. So in order to make it efficient, we need to find a middle ground, and this is where byte pair encoding comes. The technique is really good. I would recommend you to go and read, but this is out of scope for this recitation, so I'll skip that. But for now, we can see that using byte pair encoding method, we have three vocabularies of size 1K, 5K, and 10K, and you're allowed to choose any of these four, and you can go with the training. And this is given for you, so you don't need to worry about this much, but I would encourage you to go and look at the tokenizer functions, which should be in the handout. And once we do all those, we need to implement the dataset class. This class, you might be familiar with this class because you might have implemented this in all the previous homeworks. So you do the usual thing here with few extensions. So first you load the NumPy files where you are loading the inputs, and then you tokenize it. You will be using the tokenizer functions which are provided to you. And to understand which function to use, you need to go through the file. So I would recommend doing so. And then since transformers are trained through self-supervised method, you need to have two versions of the data. One is shifted version and another one is golden version. And the shifted version is one which you will be passing as input to the model, and the golden version is one which will be the ground truth. And for shifted version, you need to prepend the start of sequence token. And for golden version, you need to append the end of sequence token. And this is pretty self-explanatory. We are prepending this SOS token to the shifted version because we'll be giving the SOS first so that the model can predict the first token. And since that's the first token, that should match with the index of the golden version. And this is why we prepend with SOS token. And once that's done, you need to implement the collate function for the dataset class. So since transformers handle variable sequence input, you need to first pad them, and you need to provide lengths for mask generation. And you will be doing all these in the LM dataset script. And LM dataset script is for part one. And there might be another dataset script under the name ASR dataset, and that's for part two. But to complete part one, you just need to finish the LM dataset. And the next thing you will be implementing is two types of masking, which is causal mask and padding mask, which we'll be seeing after this. So we need causal mask to prevent model from cheating. So I mentioned that we use self supervision for training. So what we do in training is that we just give the whole input sequence, and then we'll ask the transformer to predict. So when we are giving the whole input sequence, and let's say the input sequence has 5 tokens, and we are asking the model to predict the third token given the first 2 tokens. But since all the tokens are given at once, the model can see all the future tokens. So if the model can see all the future tokens, it's not really predicting, it's just repeating what it saw. So in order to prevent the model from cheating, and in other words, in order to prevent the model from seeing the future tokens, we just create a mask so that it masks out the future tokens. For example, let's say let's take the inputs which is given on the slide. So for the first time, you just have access to the first word. So in the mask, you can see that only the 0, 0 index is false and the others are true in row 0, which means that the query at the first token can attend only to itself. But if you see the second row, you can see false on the first 2 columns. And that means that the query at the second token can attend only to itself and the first token, and it can't attend to the third, fourth, and fifth token. And this is what causal mask is. And and we are using that to prevent the model from cheating. So once we finish this mask, we also need to implement padding mask. And the reason we need to implement padding mask on top of causal mask is to prevent model from attending to pad tokens, because pad tokens we are adding pad tokens so that the GPU is able to handle variable sequence length, but that's something added by us. That's not given in the input itself. And if we are attending to the pad tokens, it means that we are diluting the attention scores. And the pad tokens don't really have any meaning. So it doesn't make sense to attend to pad tokens. So we need to make a mask which tells which part of the input is pad tokens and which part of the input are not pad tokens, so that the model knows which to attend to and which not to attend. So to this function, there'll be two inputs. One is the actual input and one is the length. Uh, the numbers in length indicate the length of the actual input. For example, the first value in length is 3, which means the first three values are the length of the actual input. The other two are the parent tokens, and the second length is 2, which means that the first two numbers are the actual input and the others are the parent inputs, which we don't need to attend to. And and you need to generate the mask based on this. For Caushwell mask and padding mask, you can write the code in less than 5 to 6 sentences each, but you need to use PyTorch functions for that. I would suggest avoiding the usage of for loops because it would make the program really slow. And there are various functions in PyTorch to support this. And there are many hints in write-up that you can go through, but I would suggest using functions like try-l, arange, and try playing around with Boolean masks. And then we need to implement positional encoding as well, because transformers do not have the notion of positions, unlike RNNs. So we need to make a positional encoding table, and then we need to add it when we are using it. And you need to implement two functions here. One is create PE table and forward function. In create PE table, you will be implementing the equations which is given here. Those are sinusoidal functions, and which was taught in class. And you need to make a matrix of shape max length and D model, where max length is the maximum sequence length and D model is the embedding dimension of the model. So you will be creating a matrix of shape max and D model, and you will be applying these two equations to find the values at respective indices. And you also need to change once you get this matrix, you need to expand this matrix to have a shape of 1 comma max length comma D model, because the positional embedding should be broadcastable. If it's not of the shape 1 comma max length comma D model, it won't be broadcastable and it will throw some shape errors. And in forward function, you will be using the positional encodings where you will add them to the input embeddings before feeding them to the model. So once you are done with all the basic stuff, you will then go ahead and implement transformer sublayers. In transformer sublayers, you will be implementing the main core components of the decoder transformer model. So here there are two main core components. One is multi-layered attention and the other one is feed-forward layer. So you'll have two classes and you need to implement them. And once you implement that, you need to implement a decoder layer. You just need to stack the multi-layered attention that you implemented in sub-layers and feed-forward layer that you implemented in a sub-layer. So uh, once you implement the transformer block, you can go ahead and stack multiple decoder transformer blocks in order to make predictions. So now you have a model, and now you need to make predictions. And once you make predictions, you need to find some way to decode it. And this is done by various methods, which was explained by Xiang. And in this homework, we'll be following two main methods. One is greedy search, and another one is beam search. While beam search is optional, greedy search is mandatory and it will be graded. And the pseudocode for greedy search is given in the write-up, and it's shown on the slide as well. And as the name suggests, you just need to pick the maximum probability at each time step, and then you need to update the sequence and the probability score. The only thing that you might notice is the apply repeat penalty function, which might be new. So we have applied repeat penalty function to penalize repeating outputs so that the output sequence is diverse. And we just reduce the probability score for that. And if you look at the overall algorithm, we just go through through multiple time steps. We get the maximum logits, we scale them based on temperature, and we find the next token, and then we update the probability score. This is all for greedy search. So once you are done, you can start training, and the training code has to be implemented in LM trainer script. You will have two training script in homework 4 lib. One is LM trainer and another one is ASR trainer. LM trainer is for homework 4 P1, whereas ASR trainer is for homework 4 P2. In LM trainer, you need to implement like three main functions. One is init function, where you will initialize the loss function, and the loss function is usually cross entropy. And when you're initializing cross entropy, you need to take care of the input size. I would suggest going through the documentation of cross entropy on how that loss function handles uh, inputs of variable length. And once you are done implementing init function, you need to implement the training loop per epoch. In training loop per epoch, what you have to do is you have to put the model in training stage, and then you need to get the generation, you need to calculate the loss, and then you need to backpropagate the gradients. This is what you'll be implementing in train epoch function. And once you do that, you need to validate it. So you need to implement validate epoch functions. In validate epoch function, you will be putting the model in inference mode, and then you will be getting the generation, and then you will be calculating the validation loss. Once these two functions are implemented, you need to train for n number of epochs. And we have implemented functions to just train for one epoch and validate for one epoch. So you just need to put the train epoch and validate epoch in a for loop to train for an epoch. And this will give you the full training code. And the main goal of this homework for P1 is for you to train a decoder model which achieves a per character perplexity of less than 3.5. Perplexity is a metric which is used for evaluating large language models, and that usually means how confused a model is when predicting a particular token. Like there are many interpretations where few people interpret as how surprised the model is, and the other way to interpret is how confident the model is when predicting. But usually uh, we can say that a model is good if it has a very low perplexity, because the model is not confused or surprised when it's predicting the next token. But if the perplexity score is very high, it means it's a bad model. And your goal in this task 2 is achieve a perplexity score of less than 3.5. And this is all for homework for part 1. If you have any questions, you can ask now. Okay, I'm assuming there are no questions, so I'll hand over to P2 team.
Sí, can you zoom out? Yeah, it's Yeah, are you able to see the shared screen on Zoom? Or is it working on Zoom? Oh, okay, yeah. Yeah, okay, then yeah, let's move on to the part two of our homeworks, which is now we're currently we've previously oh, so the recording has just started.
No, my bad.
Oh, okay, wait.
It's recording. I just joined, so it.
Oh, okay, yeah. Yeah, so on homework for part one, like what we did is basically implementing the whole transformer, the decoder only transformer architecture for autoregressive token prediction task. But on homework for part two, the main task that we're going to do is automatic speech recognition, which is basically the inputs are the speech data based on those like pre-processed embeddings that have some like meaningful information for each of those speech sequence. And then based on that sequence, you're going to translate into trans not so you're going to transcribe those sequence into a token so that you're now transforming those like speech into a text. So that's mainly how what we're doing in Homework 4 Part 2. And by doing so, you're going to use a encoder-decoder transformer architecture. So, and for the logistics, these are the main schedules. So we also have already released the homework yesterday. So you can find the Piazza post. And also you have to join the Kaggle competition in this link here. And the checkpoint deadline is also on April 10th. So you should have to complete your starter notebook and submit the results on Kaggle. And then also you have to yeah do the quiz and submit the corresponding results on Canvas. Sorry, I think on Autolab, right? Yeah. So you should do it by April 10th. And then on April 24th, you have to um, achieve like the high cutoff as hopefully and submitting those like results like you have done on like those regular part two homeworks and uh and after doing so, like you also have to submit the output zip file of your final code and your all of those like results combined, um, which are like generated by your student notebook, and you also have to submit to Autolab by 26th April, April 26th. Okay, so and the Slack submission deadline is until May 1st. Uh, and you also have the link available here. Okay, so yeah, moving on, like what we have, like as I've like briefly mentioned, so yeah, our main task is to transcribe the input speech sequence into a written text token sequence. So in order to do so, the training objective is pretty clear. It's somewhat similar to the um, autoregressive learning or autoregressive training objective, but is the difference here is that now we also have access to um, the, the full information from the source sequence. So you're also conditioning your output by the source sequence
embeddings as well. So and so you can understand like this. So for the X are the inputs from the speech, which are the source sequence, and the Y's are the tokens that you're about to predict for the text sequence. So what your encoder decoder architecture is essentially doing is to extract some like meaningful information from your speech tokens, and this is done by the encoder architecture. And then based on these, based on the final output of the encoder, you'll do a cross attention between yeah, you inject those meanings to the decoder model by cross attention. And what the decoder is doing is it similar to autoregressive training objective. You're going to sequentially predict uh, the next token based on all those previous tokens. Yeah, so yeah, this is the like essence of what we're doing with this homework. So like before going on into like those like details step by step, we will go through the overall homework structure and the workflows. So um like unlike other like previous homeworks for the part ones and part twos, the homework 4 is structured sort of like sharing the combined library. So you use the same ideal homework 4 library to implement those like basic primitives for you to build the architectures and the data set and all those like training loops. And and based on that library, you set up that library on your working directory to run your actual student notebook. So the the entire structure of how you actually set up uh, those environments is very important because otherwise your notebook cannot resolve the dependency or the relative path while importing your packages. So please make sure you have this like a proper structure to build up like this, and your student notebook should go in the um, directory level along with the same hierarchy as readme.md or like requirements.txt files. So it should be placed at the very top within the ideal homework 4 directory. And the dataset structure, like as we've explained on part 1, um, is structured as is just mainly divided as like homework 4 part 1 data and part 2 data. So the part 2 data is basically the speech embeddings data or speech features for those like end-to-end speech recognition tasks. So there are like three splits, and each of them are consisting of 80-dimensional features, filter bank features. So those are the actual data that you'll be working with. And yeah, you'll use the same homework 4 library, but you'll have to implement some of the additional components that you'll be using for a homework 4 part 2 specific task. Because now you're using a encoder decoder based transformer. So you'll have to implement those like necessary components, which we'll talk pretty soon. Yeah, and you also have to use your custom MyTorch library as well for some like necessary components, such as you have you have already implemented those like self-attention component in homework 4 part 1. So you're going to reuse that. And you have all those like sub components that are possibly tailored for a homework 4 part 1. So you can leverage those as well. And like the one of the like new components in homework 4 part 2, like unlike other like part 2s, is that it has a specific test suite within the test directory, so that you can actually test each of these components while you implement them incrementally. So while you like constantly implement like those features one by one, you can actually test them as you implement them. So that you can actually detect like where it's going wrong. So otherwise, like you go around for a long time where the error actually happens, and to debug the entire thing. Okay, and then you have to unload your like handout, which is your after you have implemented that homework for library, you have to implement unload and like sort of make your student notebook accessible to your implemented package. So the recommended way to do that, we strongly recommend this strategy, is just to use your private GitHub repository to unload your implemented components, the homework for library there, and then in the student notebook, we are providing a dedicated cell for you to load from the GitHub those packages from your private GitHub repository. So you may follow these steps. So you have to set up your own personal access token, and then you can just like simply clone your repository with this following command, with modifying this following command. You can also use like other methods, but uh, it's hard to guarantee the consistency. So we recommend this first method. Okay, so and for the setup, we don't actually recommend to use Colab and Kaggle. Or if you have a strong GPU, then you can also do it on locally. But we generally recommend to use PSC for the environment or the main compute source that you'll be working on for homework for part 2, because it requires a lot of compute in order to do the ablations and just like run the full training. So if you so we just strongly recommend to do it on PSC. So yeah, there's also some like various issues going on when using Colab. So such as like some face like out of memory issues, and some like inconsistencies on installing some packages. So PSC is a like safer way to do that as well. Okay, so yeah. So we have to, so the training process is pretty similar to like what we have like done in a homework for part 1. Um, so, but the key difference is that, like I've mentioned just previously, we also have access to those the source sequence features. So which you'll be um, integrating those necessary features extracted from the encoder layer. So for the feature extraction, you already have like provided a 80-dimensional filter bank feature. So you can just like use it right away, which is defined on our data set. And and then you'll go through the entire sequence of forwarding those features into a transformer encoder, and then uh, you obtain a final encoder output for that, and then you'll then feed those encoder output into decoder, where the decoder has a uh, it's done like similarly what you've done in part one, which is auto-regressively predicting the next token based on all those like previous predictions of those text tokens, plus those encoder outputs from the source sequence. So there's the overall flow. So and the decoder will generate the final output logic. Um, where it's also similar to the part ones where you have those obtain those logics by the final linear transformation, which is essentially you can think of it as a inverse or transposed kind of embedding the vocabulary embedding matrix. So you obtain the final logics from that. And then, yeah, same as part one, you have a like softmax plus a cross entropy loss that you actually assign a probability score based on your logics, and then you'll be able to calculate the loss between the target and your prediction. So yeah, and next is the evaluation metric. So the story so far is that we have all those predictions and made by the decoder, which are the token predictions, and we are sort of comparing that with the target. So we actually need some a form of distance to see how the model is accurately predicting or not. So the main metric that we're using here is character error rate, which are essentially comparing the character level difference between the target and your prediction. So it is defined in the following formula, which is already implemented there. So you can just like see how those like specifics are, and then you also can leverage some like decoding strategies to also produce the final text sequence. Yeah, to generate those like predictions of final sequence. So there are mainly three strategies for decoding. So the first two are the same that you have used for homework for part one, which are greedy decoding and beam search decoding. But you can also, it's very interesting to use the third strategy, which is using your language model that you have built for homework for part one as a sort of rescoring and like error correction model for your decoded final target sequence. So yeah, you can also optionally do this as well. And but you can just mainly see the initial results while you're using greedy decoding and deep search decoding as well. Yeah, so then we'll go through the main task that you'll actually be implementing each of those the corresponding components. So the task one is about building your actual components required for implementing that encoder decoder model and all those related data set and your training model as well. Yeah, so we'll go through step by step, but before we get into this, like, do you have any other like, questions regarding this so far? Okay, assuming there's no question, we can move on. So yeah, first, there are some like data pre-processing components that we have to implement. So yeah, for the tokenizer, we are actually using the same tokenizer that we use from part one, which are essentially a bypair encoding tokenizer. And well, we are actually providing the tokenizer here, but you should be aware of the tokenizer, to each of the tokenization strategies, which are character level tokenization or subword tokenization. So yeah, like we have like um, explained on part one section, we have those like four options mainly, but it is very important to choose the right type of tokenization because it will affect on the overall sequence length, and that will be like amplified during while you're doing beam search, like your your training time or evaluation time gets like exponentially larger. So you have to be aware of that and choose the right strategy. And you also have to implement the data set part as well. So you, yeah, these are the specifics of the data set, so that you can actually go walk in through those. Yeah, walk through those, and yeah, and you have those within the ASR dataset class. This is what you'll be implementing for homework for part two. So once so you have to load these data set, which are essentially the features, the filter band representations, um, and then you have to tokenize them to using those tokenizer that we have mentioned just previously. And then you also apply those normalization strategies to each of those features. Yeah, which are some of the examples are here, but you can also try other sort of normalization strategies if you want. And after that, you apply the spec augment data augmentation strategy only for training, which are time masking or frequency masking. Like it's similar. It's similar to like what you've done for like homework one for part two, or like other previous part two homeworks regarding the speech data set. And then you'll like similar to the part one, you'll also have like two versions of the tokenized transcript. So this is what the final decoder is doing, which is a like shifted version, like the right shifted version of the target sequence, which starts but with a startup sequence token, or the SOS token, which is what the decoder actually sees. And then the golden version is the actual target, which is a sequence that starts without a start of sequence token, but ends with this EOS, end of sequence token. And then you'll also have to implement a collate function as well. This function is essentially handling those like features, padding those features, and to match the length equal for throughout the batch. So you'll also have to like handle the dimensions really carefully here as well, and especially those like while you're dealing with this data set or this processing these data sets, you'll be aware of the space token as well, because like in my own experience, like that triggers some kind of specific errors while if you're like mistakenly dealing with those specific tokens as well. Okay, and once you do that, you can also like run those corresponding tests. Yeah, test script that is integrated in your library as well. Yeah, and it is also like implemented in the notebook file as well. So you can just like so, just run it directly for testing your component. Yeah, next is your model implementation. So you'll be yeah, to repeat again, you'll implement a encoder decoder transformer for this. And so you have to implement some um, necessary primitives for building up this architecture. So but the good news is that you already have some core components that you already implemented for while you're doing homework for part one. So as you can see in this figure, those like colored parts are the ones that you already have implemented for homework for part one. So the rest of the things that are the things that you should be implementing, which we'll go through one by one. Yeah, so the first sublayer that you'll be implementing is the cross-attention layer, which is essentially applied on this specific cross-attention component within the decoder architecture. So this is actually this almost similar to the self-attention, but the only difference is it would be that the keys and values are coming from the final encoder output, while the query is coming from the decoder, the previous self-attention output of the decoder. Yeah, so once you do that, you will also implement a higher class of this cross attention, which will integrate that cross attention to your decoder layer. So in that way, you create a transformer cross attention decoder layer within the decoder layers.py. Also, you will have to implement a specific encoder layer architecture in encoder layers.py file, which which utilizes a self-attention, but here it doesn't have to be masked. So that's the difference that you have been used for homework for part one. So it is a unmasked self-attention based transformer architecture. And finally, you'll once you have implemented those successfully, you'll combine those two encoder and decoder architecture to create a full encoder-decoder transformer, which you'll be implementing in the transformers.py file. Yeah, and in the transformers.py file, the class that you'll be implementing as a full encoder-decoder transformer, there's a dedicated speech embedding layer, which you'll be like pre-processing the speech embedding that is defined in your dataset. And what it does is it's consisting of those sublayers that sort of preserve this feature information, but sort of like contracting the time dimension scale. So you'll handle those input sequence or the source sequence more efficiently. Yeah, and you also have the positional encoding layer to inject the positional information as well. Yeah, and then those like previous modules are the ones that you already implemented previously, and also an embedding layer is required, as well as the final linear layer to create the logics. And you also need to have a layer norm for all those like residual connection and post-processing those residuals. Yeah, you also optionally have a dropout for regularization, and it is known to improve your model performance, so you'll be adding that as well. Yeah, I think the beam search decoding here is also optional for you to implement. So the main decoding strategy would be just greedy decoding, but it is highly recommended for you to implement and apply those beam search decoding as well, because it in practice will enhance your final model performance, especially in terms of the final prediction outcomes and the CER scores. So there's we have provided a pseudocode for building your beam search, so you can leverage this while you're building. Yeah, and then you'll so those are all those like main components that you be implementing. But there's just one thing left, which is ASR trainer, where you'll be using this trainer class to actually train your model doing in your student notebook. So yeah, you'll have so most of the parts are already filled in, but there's some like missing parts which we marked as to-dos. So for those parts, you have to fill in those necessary components, which are actually specified here. So yeah, and once you also have done those implementations for the model architecture and this trainer as well, you have those corresponding tests those test suites as well, so you can also run the test before you actually train your own model. And it's important to note that you must be optimizing your model by character error rate, CER, to actually align with your final performance metric and your training and your exact training. So otherwise, the model will converge, but it will not like optimize the CER, which is not the desired way of our training. So, and once you've done that, you submit the results in Kaggle and under this form, but this is already provided, so you can just run the cell that is provided for evaluating and submitting on Kaggle. So until April 10th, you'll be submitting your initial results on Kaggle, and the early cutoff is to achieve a CER below 50% on the public subset of the test set. So in other words, you have to see your public score on Kaggle, which is lower than 50. And the high, medium, and low cutoffs will tentatively be released after the initial early cutoff deadline on Piazza. So you should be able to check there after April 10th. Yeah, before we move on to the training and inference techniques or strategies, we can also like mention some like tips um for handling those feature representations. So like as I like mentioned before, it is important to choose the right strategy of tokenization, because you don't want the sequence to be extremely long, and you want each of those tokens have a meaningful information containing. So please be aware of this and choose the right one. And you can also sort of decrease or contract along the feature dimension. But this is yeah, usually I just like not recommend this. You can just use the full feature space as well, and that's like just sufficient. Okay, um and like as I said before, uh in the speech embedding module, you'll essentially be downsampling those input speech, input speech sequence or each of those representations along the time dimension. So in that way, you can sort of contract and like sort of build a more compressed representation, which will make your training much more efficient. And you can do that by those sequence models or some convolution models. So you have that you can build a like CNN based downsampling or LCM based downsampling models in order to do this. Yeah, and then we'll move on to discuss some training strategies and some inference strategies. And I think Mengshun can take care of this. Yeah, before we move on, do you have any other questions? Yeah, if not, we can move on. Okay. Mengshun, do you want to share your screen or can
Oh,
you just
hi,
use
Eugene.
this?
Can you hear my
Okay.
voice? Yeah, I want to send share my screen. I have sent a request. Okay.
Oh, okay. I think I'm not the one who can manage that share screen, so I think I can stop sharing my screen.
Okay, thank you.
Okay.
Okay, can you see my screen now? Okay. Okay, hi everyone. Thank you so much for just going through the write-up. Now I'm going to introduce some training and inference strategies. You can also find all of them in your write-up under section 7, tips and tricks. Let's start with the training strategy. I will go over 3 different strategies for training your transformer model in homework 4. These strategies are cold start, pre-trained decoder initialization, and progressive training. So for the first strategy, which is cold start, this is the simplest and most straightforward approach, just like what you've done in previous homework P2s. It is already provided in your notebook. So if you just follow the notebook, you are already using these strategies. In cold start, you train the entire model from scratch. That means both the encoder and the decoder are randomly initialized, and you optimize everything together using the standard training loop. There are no special tricks here, so it can serve as a good baseline. It's easy to implement and useful for understanding how the model behaves, but it may take longer to converge and might not achieve the best performance compared to more advanced strategies. Now let's move on to the second strategy, pre-trained decoder initialization. So the key idea here is to reuse what you already built in homework 4 P1. In P1, you train a decoder-only transformer model. Instead of discarding that, you can use it to initialize a decoder in your encoder-decoder model for P2. So rather than starting from scratch, you're transferring knowledge from a pre-trained model. This is a very common idea in deep learning. There are 2 main advantages to this approach. So first is it can significantly speed up convergence because the model is not starting from random ways. Second, it can usually improve your model performance since the pre-trained decoder has already learned some useful language patterns. And to apply this strategy, there are 3 main steps. So first, you need to initialize a model with pre-trained weights. This means loading the checkpoint from homework 4 P1 and use it to initialize the decoder part of your new model, including the components like feed-forward networks or attention layers. Next, you need to, like during the early stage of training, you need to freeze the pre-trained decoder weights. At this point, you only train the encoder and the cross-attention layers. The reason is that you want to preserve the knowledge in the pre-trained decoder and avoid damaging it too early. And finally, after the model has adapted a bit, you unfreeze all the layers and fine-tune the entire model together. In this stage, both the encoder and decoder are updated, and sometimes you may use a smaller learning rate for the pre-trained part to keep the training stable. Okay, then for implementation, this part is not provided in the notebook, but there are some helper functions you can use. For example, you can use the from pre-trained decoder function. It can help you initialize the model with a pre-trained decoder and load the corresponding weights. And you can also use a create optimizer function. It can be used to set different learning rate for different part of the model, especially when some layers are frozen and others are trainable. But before using this strategy, there is one important note. Please keep in mind, the pre-trained decoder must be compatible with your new model. That means the dimensionality must match, and you must use the same tokenizer and similar architecture setting. This is very important. Otherwise, the weights cannot be loaded correctly. Now let's move on to the third strategy, progressive training. This strategy is a bit more advanced, but also very powerful. The main idea is that instead of training a large and complex model from the beginning, you start with a small and simple model and gradually increase its capacity during training. In other words, you make the task harder step by step. This approach has two main advantages. First, it reduces the risk of overfitting early in training because the model is small and simple at the beginning. Second, it can speed up the early training process since fewer parameters mean faster computation. And to understand this strategy, we need to think about what difficulty means. In this context, difficulty can come from several sources. It can come from increasing the size of the dataset, increasing the complexity of the model, or increasing the strength of the regularization, such as dropout or label smooth. At the beginning, we keep everything simple so that the model can learn basic patterns. Then as training progresses, we gradually increase the difficulty. And there are different ways to schedule this progression. One simple way is to use a fixed schedule. For example, you can increase the number of layers every few epochs and also gradually increase regularization. Another more advanced way is to use self-paced learning, where the model's performance determines when to increase the difficulty. Now let's look at a recommended schedule. The idea is to start small and gradually increase the model's capacity over time. And here is an example. At the very beginning, you start with a very small model that has only one encoder layer and one decoder layer. At this stage, you do not apply any phrasing or regularization, and you only use a small portion of the training data, for example, 20%. And this makes the learning process very easy and stable. Then in the next stage, you increase the model size to 2 layers for both the encoder and the decoder. At this point, you freeze the previously trained layers so that their knowledge is preserved, and you still avoid using regularization. You continue to use a small subset of data. After that, you increase the model to 4 layers. Now the model is more powerful, so you can start introduce more some regularization. such as small dropout rate, and you still freeze the earlier layers to stabilize training. Then you can expand the model to 6 layers. In this stage, you may train only the newly added layers while keeping earlier layers frozen, and you can further increase the dropout rate. Finally, in the last stage, you unfreeze all layers and train the entire model together. At this point, you apply stronger regularization, such as higher dropout rate or label smoothing, to improve the generalization. And also, like the second strategy, progressive training is also not provided in your code notebook. So you need to implement yourself. But here's also some functions you can use. For example, progressive trainer class. It can help you define the training schedule and train the model. And you can also use a create optimizer function, which we mentioned before, to set different learning rates for different parts of the model. And here's one final note is that all of these 3 strategies are not mutually exclusive. So in fact, you can combine them. For example, you can start with a pre-trained decoder and then apply progressive training on top of it. This combination often gives the best results because you benefit from like both prior knowledge and a stable training process. And to summarize, cold start is the simplest baseline. Pre-trained decoder initialization helps you train faster and let you leverage your homework for P1 and can usually achieve better performance. And progressive training helps you train more efficiently and avoid early overfitting. So depending on your time and goals, feel free to try these strategies individually or combine them. And feel free to explore more training strategies. Okay, now that we've gone through the training strategies, let's move on to the inference part. You can also find this in your code notebook under inference section. And in inference, there are mainly 2 strategies you can consider in this homework, the decoding strategy and the fusion strategy. So the decoding strategy determines how the model generates tokens, for example, greedy search or beam search, and the fusion strategy determines whether you use an additional language model during inference, which is called shallow fusion. Now let's see how this is actually used in practice. So during inference, at this stage, we assume that you have already trained your model. The main thing you need to pay attention to is that the recognition config that you pass into your trainer.recognize function. This config controls how your model generates the predictions. And in this config, like parameters like temperature, repeat penalty, and also beam width, they all affect the decoding process. In particular, beam width is very important. If you set beam width to 1, it falls back to greedy search. If you increase the beam width, you're using beam search, which usually gives better results but requires much more computation. So the computation cost grows quickly with both the beam width and the sequence length. You may need to consider both when you implement in homework 4P2. And so for cases like character level tokenization, since each sequence is long, beam search can take years to run. So in these cases, you may want to avoid using beam search. And in general, the choice of beam width is trade-off between performance and computation. So you should adjust it based on your available compute and inference time. And other parameters like temperature and repeat penalty, they also play a role in the decoding strategy. So temperature controls how random the predictions are, and the repeat penalty helps reduce repeated tokens in the output. Then for fusion strategy, you can optionally use shallow fusion, which allows you to use the pre-trained decoder from your homework 4P1 during inference. This is different from what we discussed before in training. Like during training, we were effectively doing something like a deep fusion, where the decoder is integrated into the model and trained together. But here, in inference, we combine the pre-trained decoder with the model outputs without retraining. So here, the LM model is a pre-trained decoder that you will pass in as a language model. And the LM weight, it controls how much influence that the language model has. So the final prediction is obtained by combining the outputs from both models. And after you set up all this config, you simply pass it into the trainer.recognize function to generate predictions and then submit the result to Kaggle, as you usually do in previous homework P2s. That's all for the training and inference strategies. Now I'll pass it to Pengyu to work through the code notebook.
Hello everyone. I will walk you through the starter notebook. So because of the difference between homework for part 2 and previous homeworks, the notebook does not contain most of the implementation. You must first implement the dataset and trainer in the homework for lib, and then after you finish implement them, you can come to the notebook and start your training. So first of all, the setup, you can choose Colab and Kaggle, but for homework 4, the most recommended computation resource is PSC because it has V100 and you can save your time on training and some and inference. And for setting up, it's almost the same with previous homework P2s, but there is one difference is that you need to get the repository that you completed your homework P1 and P2s, that is the homework for lib. You need to get that repository, or you can also manually maintain the folder, and you must make sure that you're inside the the folder when you run the notebook. And Kaggle authentication is the same. And get data. And another difference is that we import all the necessary contents that we implemented from homework for lib. And this imports code here. And when you try to modify your implementation, your homework for lib, you must re-import them here so that your modification take effect. And here, so homework for homework 4, the notebook acts more like a interface that you use for your training. So here's a very detailed config table that you can change. So first of all, for tokenization, you can change the token type here. Just change the 5K here to whatever you want. Also, I want to know that the char tokenizer is not recommended. It will increase the sequence dense by a lot so that the inference time of beam search might be way too long for you. And for dataset part, typically you don't need to change except for the root. It just depends for where the root path or where you download your data at. And this is the way how you normalize the data. So the global MVN means it uses the global mean and variance to normalize the data. And 8 is the feature norm, and you should change this. And here's some data augmentation. You can set it true, and it will add some frequency mask and time mask here. And here is where you configure your model. So for homework 4 P2, we have a encoder decoder transformer. So for the input dimension, it is this feature, 8 total features. And what does time reduction means? It means that for example, for the 2, you reduce the total sequence to half of its length. And the reduction method is either convolution whether a CNN or a LSTM or we use both methods to do the time reduction. And here is the transformer architecture parameters. You can change model dimensions. You can change the number of encoder layers and decoder layers. And you can change the number of encoder heads here and decoder heads here. And you can change the feed-forward dimension for encoder and decoder. And you can set skip encoder P. This is what positional encoding for encoder and decoder. So here should be the main part that you focus on when you try to do some ablation, whether you want a wider model or a deeper model, whether you want a higher feed-forward dimensions or different attention heads, you can change it here. And here is a dropout rate and layer dropout rate. You can increase them. And weight tying is a method that used to save parameters that you might want to use when you're trying to save some parameters when you're very close to the parameter limits. And here are some training parameters. You just need to put in some your one to be information here. And for loss, here's label smoothing. Label smoothing is a way to is for cross-entropy loss that where it's mostly labeled to for not overfitting, and the CTC weight here is how are you going to weight your CTC loss to your total loss. For example, the 0.2 here means CTC loss is 20% of your total loss. And optimizer, you can configure your optimizer here, and for scheduler, you can choose from reduce R cosine or cosine 1 here, and you can configure it more detailed in each section. And after that, you need to run this to save it. So every time you edit your configuration, you always need to run this so that is saved. And here is the tokenizer and datasets that you implemented, and data loader to load data. And don't forget to verify whether your data is loaded correctly. Also, in this notebook, we provided a way to let you try to test your implementation is correct before you started training. So it is in the implementation section, and it just runs a test that it is in the homework for lib test folder here. And here is the part to calculate max length. And we start 1B and start training. Note that the training will create a new directory in the excepts folder, which is in your IDL homework for lib. So note that. And here is the CodeStar trainer we provided for you. And trainer is ASR trainer. And for you when I'm trying to implement our training strategy, you can change the ASR trainer into the progressive trainer. And don't worry, the progressive trainer is we have implemented for you. So you can try. And here, scheduler, and you can print a schedule so that you can see whether your scheduler is what you want or not. And here you start the training. Notice that you can change epochs here. And after the training, you can see the inference code here. And Mengchen have just displaying in most of them. So temperature here is 1.0 is normal, and for a value larger than 1.0, you increase the randomness of the output. And repeat penalty is that 1.0 is no penalty, and for higher value, it penalties the repetitions of generated content. And it will generate a CSV file. You can submit here, but you can also manually submit by yourself. And you can manually inspect the results here to see whether it matches your expectation, because sometimes even if you pass all the tests that we provided, it can still have some errors. So if you can always manually inspect, because it just generated, that is a human readable text for each person's for transcription. Yeah. And then you see AutoLab submission. You can just set the model here, and you add a README here, and you can fill in everything here, and it will generate a zip file for you, and you can upload it to AutoLab. And that's all for the student notebook here, and that's all for Homework for P2's bootcamp.